Welcome. This video is going to look at the main ideas from Section 4 of Chapter 4 of the Brown SL Chemistry book. So in Section 3, we took a closer look at covalent structures. And in Section 4, we're going to look at this idea of intermolecular forces and how that affects covalent properties. So ionic compounds exist as a lattice of alternating cations and anions, so there aren't any distinct individual molecules. For example, one NaCl, one Na is surrounded by 6 chlorine, and one Cl is surrounded by 6 sodium ions. One on each side, think of it like a die, the 6 different sides to the cube. So it's being pulled by all 6 of the opposite ion at any time. But covalent bonds exist within a molecule like H2O. And so you have one H2 molecule and then a neighboring H2O molecule. And with intermolecular forces, we're talking about the forces between these molecules. Of course, there's a force within the molecule. These chemical bonds are known as intramolecular forces, or the covalent bond, and that holds the atom together. And its strength is going to depend on the polarity of the bond and the size of the atoms, etc. But what we want to talk about in this section is the intermolecular forces that exist between the molecules. So what kind of forces are there between these water molecules that hold a water droplet together where there's millions of water molecules? So there's 3 types of intermolecular forces which determine the physical properties of covalent compounds. There's London forces, which are also called dispersion forces, or sometimes even van der Waals forces. IB and myself will tend to call them London forces or dispersion forces. Then there's dipole-dipole forces, and finally hydrogen bonding. So these London forces or dispersion forces, sometimes they consolidate the name and call them London dispersion forces, or LDF, which is a nice short way of doing it, are also known as instantaneous dipole-induced dipole forces. And even though that's a very lengthy name, it really tells what's going on. There's a very instant or short-lived induced dipole force that attracts the molecules to each other. So what exactly does that mean? Well, first of all, it occurs in nonpolar molecules where there is no charge separation. The electrons are shared equally, so they don't hang out more at one atom than the other as a general rule. So there's no positive end and negative end, or no permanent dipole. However, at any instant, the cloud of charge, that's the bonding pair of electrons, think of it as like a cloud of gnats, they may be hovering closer to one of the atoms than the other. When that happens, it creates a temporary dipole within that molecule, which then sets off this domino effect. Because the electron cloud is closer to the left end of this molecule, let's look at oxygen. So oxygen's double bonded to itself. If at some moment these 4 shared electrons were hanging out slightly closer to this oxygen, it would set up a slight negative charge and a slight positive within this oxygen molecule. Well, because these electrons are crowding this end, in my next oxygen molecule, that would tend to repel those electrons toward the other end and set up a temporary dipole in this end. And then that would continue on, kind of ripple through the surrounding molecules. It's going to repel these and set up a positive end here and a negative. And you can see where it's just this very quick, very short-lived induced dipole force. So this temporary dipole within the molecule sets up just a very quick, very weak force between them. So here's an example, perhaps a little better illustrated than what I just showed you, but your electron cloud typically is evenly distributed. At some instant, more of the electron cloud happens to be at one end and sets up a negative charge on that end, which then induces a positive charge on the neighboring molecule. And then the attraction between those resulting dipoles is called the dispersion force. These are the only forces that exist between nonpolar molecules. They also exist in polar molecules. They can also arise in polar molecules, but they're so weak compared to the other forces in polar molecules, we don't really take them into account much. But in a nonpolar molecule, they're the only game in town. So a couple things to realize. They increase with molecular size. Both mass and more electrons seem to increase this force. And it's expected they're not very strong. So most nonpolar molecules are gases at room temperature. That means they have low melting and boiling points. They're highly volatile, which means they change to a gas easily. And they're also highly compressible. Okay, nonpolar means it's easy to squeeze these molecules very, very close together because they don't have dipoles pushing back. So that's actually a very good thing that you can compress these gases for transport. So then dipole-dipole forces, these occur among polar molecules where you do have charge separation and a permanent dipole. You have one end of the molecule that tends to be positive, the other end that tends to be negative. So then the opposite charges on neighboring molecules attract each other. And now we call this a dipole-dipole force. So instead of being an instantaneous induced dipole attraction, this is a permanent dipole-dipole force. So it's typically going to be quite a bit stronger than dispersion forces, but it does depend on the distance between the dipoles and how polar that bond or molecule is, and also the orientation of the dipoles. What's the shape of things going on? So a higher melting point and boiling point than nonpolar molecules typically, and usually they're going to be soluble in polar solvents like water because remember, like dissolves like, and water's polar, so it will tend to dissolve other polar substances. Dipole-dipole forces are also considered a van der Waals force. The last intermolecular force to talk about is hydrogen bonding. And I prefer to call it hydrogen bonding than a hydrogen bond so that it reminds me it's not a chemical bond like a covalent bond or an ionic bond or a metallic bond. It's an intermolecular force. It happens to be the strongest one. And it occurs in a unique situation. And it's when you have hydrogen, which is a really small atom, and when it bonds with a really electronegative atom, which the three most electronegative are fluorine, oxygen, and nitrogen, it creates this really strong dipole-dipole force called a hydrogen bond. And the reason for it is that the bond itself is so polar, it's nearly ionic, and so the hydrogen atoms in these pictures I've got showing here basically are left just with the positive protons. So these are very positively charged, whereas the lone pair on the oxygen are highly negatively charged. So it's almost like having an ionic lattice here. And the attraction between neighboring atoms, which is shown with these dotted lines here, is nearly as strong as the intramolecular force. So it allows hydrogen to strongly attract a lone pair from the neighboring oxygen. It causes much higher melting point and boiling point than you would expect for its mass. For example, water freezes much colder than most covalent substances, and it boils much higher. And you notice that each water molecule can actually form 4 different hydrogen bonds. So if I look at my hydrogen bond down at the bottom here, the 2 hydrogens have each formed a hydrogen bond with neighboring, but these 2 lone pair can also form with another neighboring one. So if I draw in my other 2, you can see there's a total of 4 different hydrogen bonds for this one water molecule. And this is why ice actually needs to expand or needs more space when it forms than liquid water does, because now it's going to be in a fixed position and it needs to have this distance for these hydrogen bonds to set up. Hydrogen bonds are also responsible for making hair curl. It's this cross bonding that goes on. It's even responsible for the double helix, the curled structure of DNA. So although hydrogen bonds are stronger than dipole-dipole, which are stronger than the London dispersion force, remember covalent bonding, holding the molecule together, is still 15 to 20 times stronger than most of these intermolecular forces. And ionic and metallic bonds are even stronger than this. So it's only an intermolecular force. It's not a true chemical bond. And also keep in mind that nonpolar molecules have only the London dispersion forces, but polar molecules have the dipole-dipole and some London dispersion force at work. And it means a molecule with hydrogen bonding also is considered to have London dispersion forces and dipole-dipole forces going on as well. So how does this affect properties? Well, changing state, like melting or boiling, involves separating the particles or overcoming the forces holding them together. In the case of both melting and boiling, you need to put energy in and move the particles further apart. So covalent substances in general will have lower melting points and boiling points than either an ionic or metallic substance. So most of them are liquids or gases at room temperature. The other thing to keep in mind is that all intermolecular forces increase with an increase in molecular size or mass, as well as an increase in polarity. So solubility, the general rules for solubility are that like dissolves like, so nonpolar solutes can create temporary dipoles in nonpolar solvents and allow dissolving to occur. Polar compounds, on the other hand, dissolve in other polar compounds, either dipole-dipole or hydrogen bonding, or even ionic. So many large molecules actually have both a polar and a nonpolar end, but if the large molecule is mostly nonpolar and only the one end is polar, like an OH group attached to the end, then it's only going to be slightly soluble. That's why it's hard to say something is or isn't soluble, because sometimes it's slightly soluble. So this is often the case with stuff we can't wash off our clothes very easily, like grease. It probably is a mostly polar molecule with just a very small polar end. I say it's mostly nonpolar molecule with just a very small polar end. Another thing on solubility is giant covalent structures don't dissolve very well in polar or nonpolar. And in the case of diamonds, this is a good thing. You don't have to worry about getting it in, getting your fingernail polish remover on it or getting it in water. It doesn't dissolve well in anything. And that's because they're covalently bonded throughout the structure, so it's not a matter of intermolecular forces being separated. You actually have to break the covalent bond. Another thing to point out with solubility is that many substances in our body are polar, and they move around through the watery fluids and cells in our bodies, okay? And that's a good thing. But when you hear about this blood-brain barrier, which I see barrier didn't quite make it onto the slide, but you hear about the blood-brain barrier, and the idea there is that there's a fatty membrane around your brain, which is nonpolar, and that's done to prevent many common substances from crossing into your brain. So it's much more restrictive when you get to these nonpolar or fatty membranes. And then the last property is electrical conductivity. Covalent compounds don't have ions. They don't have ions that are free to move, and they don't have delocalized electrons that are free to move, even hydrogen bonds, as dipolar as they are. So they are not going to be good conductors. The only time a covalent compound might be a good conductor is in the case of some of these giant covalent structures, like graphite or graphene, and then you may see some conductivity, and usually they're semiconductors where you can enhance that conductivity. Also, the other case where we see some conductivity is with acids, which is hydrogen covalently bonded to another nonmetal. When acids dissolve in water, they actually form an H plus ion and an X minus ion, X representing the nonmetal. So acids also make good conductors in solution. But as a general rule, covalent substances are poor conductors.